Okay, so we're going to look at exam 2 from Organic Chemistry 2, and this exam was covering basically chapters 15, 16, and 17. Um, so let's look at page 1 here. We're just asked to fill in the major products and for the following reactions. So we'll start here at the top. We notice we have a diene, right? Got a diene here. Got a dienophile. Dienophile, there it is. Right, and we basically heat this up. This is just classic Diels-Alder. So let's start to slap some labels in here, right? So we'll do our 4 carbons there from the diene. We'll do these in red. All right, there's our dienophile. We know those gets added, right? So we know we always make a 6-membered ring. We know we always make a double bond between those two carbons right there, between carbons 2 and 3. Right. So now we got to fill in the blanks off of carbon 1. We've got our methoxy group, and we've got a CH3 group here, right? And then on our dienophile, since it's asymmetric, we have to pay attention to 1,2 versus 1,4 additions. And since, excuse me, and since we since we can only do a 1,2 or a 1,3 in this case, we know we're going to prefer a 1,2 addition. So we are going to have our final product like this, right? If we want to just come back, right, we can number all this stuff here to make sure we have everything. So classic Diels-Alder, means we got to pay attention to the 6-membered ring that's formed, the wedge versus the dash, whether it's a 1,2 versus a 1,4 preference for our product there. Okay, next. So we've got a 6-membered ring with an alkene. We've got NBS, right? This is our allylic. That's our allylic bromination. So we're going to add a bromine in the most stable allylic position. It's going to be right there. We throw in some T-butoxide, right? That's our way of making the less substituted double bonds. So now we've got a 1,4 unsaturated double bond, and we put some HCl and we warm it up, right? That means we're going to, we're going with our thermodynamic product here, right? So we end up doing a 1,4 addition, right? So we're likely going to end up with that guy right there is what it is. Again, we could always have a mixture of products depending on what you specifically wanted, but that was kind of what I was looking for in this case here. All right, let's move that out of the way. Next, so now we have a set of aromatic compounds, and for this guy here, we're putting it under acidic conditions, and for this guy here, right, we're putting under basic conditions. So we're asked what happens. Now we know with aromatic rings, right, the electrons that are involved with making the aromatic rings are, they fall under a specific class of reactivity, right? They have specific reaction conditions for that to happen. And so we have a choice, right? If we're looking on the left-hand side here, we have this 5-membered ring with the 2 nitrogens. I filled in the red and the blue electrons there, right? The red and the blue lone pairs. So the red lone pairs on that nitrogen, along with my double bonds that are in the ring there, right? Those form that's a total of 6 electrons. And those electrons, remember, that's our Huckel number, right? Our 4n plus 2, right? So 4n plus 2, right? And n equals 1 in this case, right? So 6 is a Huckel number of electrons, which is one of the requirements to have an aromatic ring. The other requirements is that it's a flat planar compound, right? That we have a continuous pi system, right? And so those are all held true in this case. And so what that means for us is that this lone pair in red is not reactive, right? And what I mean with that is it's not reactive in the same way that a traditional lone pair on a nitrogen would be reactive, right? That lone pair right there is part of the aromatic ring. So if we want to react those lone pairs, we're going to have to do something drastic, right? We're going to have to put under extreme conditions to react and to break apart that aromatic ring, right? Whereas the ones in blue here, right, those are going to be more reactive, right? Those blue are not involved with the aromatic ring. They're orthogonal to the ring, right? So these are going to behave just like standard nitrogens, right? Remember nitrogens with lone pairs, we think of them as organic bases, right? They're organic bases. They're on the hunt for something acidic, right? So this first question here was asking, right, can you recognize what makes an aromatic ring? And do we remember, what happens with aromatic rings in terms of reactivity and all this? Okay, so we're going to react our blue lone pairs there because they are not part of the aromatic ring, right? And they are basic, right? So let me just clean some stuff up here. All right. So that blue lone pair there is going to go after our acid, right? Our HCl, right? So we're just going to do a simple acid-base reaction. Right, where we end up protonating that side there, right? So we end up making that, right? This is our buddy imidazole, right? This 5-membered ring here with 2 nitrogens, that's our buddy imidazole. That's a very common organic reagent, a very common biochemical reagent too, right? It's found in one of our amino acids. So you guys will learn a lot about that. And the important part to remember is that one of those nitrogens is basic and the other one isn't, right? So the nitrogen in blue there is the one that's going to react to pick up any acidic hydrogens that are around. Okay. All right. So we move over here, right? We move over here. We're given sodium hydroxide, right, and some water. And basically what we're going to see is, sodium hydroxide is a strong base. It's on the hunt for something acidic, right? We're not heating anything up, so we don't have to worry about any of these other reactions that might happen, that we learned about. But that's for a different time. So we're a base, right? This is a base right here, right? So it's on the hunt for the most acidic hydrogen. We've got several choices for acidic hydrogens here, right? We'll quickly run through them, right? We've got all these hydrogens that are here on the aromatic ring itself, right? Now, those hydrogens aren't particularly acidic, right? We're going to have to put a very strong base in to deprotonate any of those, and we just don't. And hydroxide is not a strong enough base to really accomplish this, especially under aqueous conditions, right? All right, so we don't have to worry about that, right? We've got these hydrogens over here. For our purposes, we can go ahead and assume that those are not acidic either, right? These are just plain old alkyl hydrogens, not very acidic, right? And so we're left with our choices of our hydrogen here in purple, right? Or we have our hydrogen here in red, right? So our base is going to go after one of those alcohol hydrogens, right? So as with always, right, let's see what happens, right? Let's see what happens in both of those cases and see if we can make an assessment about what's better, right? So let's go after that red. Let's go after that red hydrogen there, right? So let's do that acid base right there. Okay. Oops, sorry, I forgot about that there. Okay. So what did we do, right? We ended up trading a sodium hydroxide for an alkoxide there, right? Okay, fair enough. Nothing remarkable about that. We can't shift, right? We can't shift that minus charge around anywhere, right? Let's pursue this now. Let's see what happens here. So if we do that acid base there in purple, right, we're left with an oxygen with a negative charge also. Say, okay, well, in both cases, right, with the purple, and let me just draw this in red down here so we're following, right, with the purple and the red, right, we're both left with an oxygen with a negative charge. but there's got to be an answer, right? There's got to be something we can pay attention to see which one's going to be our answer. Well, let's take a look at our purple here, right? What's different about our purple as compared to our red? Well, we should be able to see here, right, that we can start to draw resonance structures. So if you follow our purple arrows here, excuse me, I still have got my cold that I'm fighting with here, right? We can see we can start to draw resonance structures. And so if we wanted to follow this all the way around, which for simplicity's sake we won't in this case, right? But we could start to draw a resonance structure and delocalize that minus charge all the way through the ring, right? So what does that tell us? Well, remember, anytime we can spread a negative charge around, right? Anytime we can spread a negative charge around, right, that's going to be a stabilizing effect. So our purple hydrogen here is going to be far more acidic than our red hydrogen is. And in fact, this is going to be our answer right here, right? We can deprotonate that oxygen with a negative, that alcohol there that's attached to the ring. A much more acidic hydrogen than a regular alcohol is. Okay. So remember what we've been talking about all semester long with acid-base reactions. And if I'm asking you an acid-base reaction, well, do an acid-base reaction and then do an assessment, right? Where does my negative, where's my positive? What does that tell me, right? Which one of my hydrogens is more acidic? Can I spread out charges? All these kind of things that go into following along with an acid-base reaction, okay? All right. Oh, sorry about that. Okay, moving along here. So we've got our buddy anisole, right? And the first one here, we're doing a aromatic halogenation. Nothing fancy about this. We just got to add that chlorine. We can either add it there or, right? Let me just change colors, right? Or we could add it in the ortho or the para position, right? This is an activating group, right? This is activating group, so we're going to add ortho or para. So you could pick either one of them. We'll just go with the para position here because it's probably slightly favored over the ortho just because of sterics. Okay, so we take that compound there, and in the next reaction, we're putting nitric acid and sulfuric. So this is nitration, right? And so we're going to add a nitro group, right? We're going to add a nitro group. Ortho to our activating group. Remember, halogens are deactivating, but ortho para directing, right? Halogens are deactivating, but ortho para directing. A anisole there, right? Our oxygen is activating, so that's going to be the one that kind of dominates our reactivity, right? The activating group tends to dominate over the deactivating group. And remember, we talked about why that is, right? You take a look at the intermediates and which step of the mechanism, right, is involving the activating or deactivating group and what that causes, right? So there's one of our answers. We got a nitro and a chlorine. This likely won't react anymore, right? We got two deactivating groups there now with the nitro and the chloro, so we don't have to worry about further reactions. All right, lastly, we've got this bis aromatic compound here, and we've got a cyclical ester there, right? And so really what we're asking here is, right, we've got this carbon in red that's attached to this aromatic ring here, right? And we've got that oxygen in black, which is attached to this aromatic ring here, right? Now remember, typically carbonyls and carbonyl carbons are deactivating groups, right? They're deactivating groups. So our aromatic ring there in red, right, is a deactivating group, right? So it's a deactivated aromatic compound. But however, the ester, right, the oxygen in black there is likely activating that ring that it's attached to. So we're going to add our group to this aromatic ring here, likely somewhere that's either ortho or para to the activating group, right? Now the conditions that we have here are our sulfonation. So we're just going to draw our compound back in. right? That's what we got. And we're just going to add our SO3, right? Actually, excuse me, right? Our SO3H here, either there, or again, we could probably add it here also if we wanted to. Okay, so likely that's going to be, either one of those is going to be our dominant products in this case. Okay. So these last two questions, we're just dealing with activating versus deactivating groups and aromatic substitutions. So I'm going to zoom out so you guys can see all of page 1 here, and we'll pick this up in the next video.